Okay, good morning, everyone. Uh, I'm Dr. Anga Rodrigo. I teach in the Department of Electronic and Telecommunication Engineering. So I will be teaching you the computer vision part of this course. So it is a very exciting part of the course, in my opinion. I think you will learn quite a bit of new things in this. So I studied at Morato University, of course, and then went for my higher studies at Western University of Canada. So that was from 2003 to 8. Uh, so there I studied computer vision. So from 2008, I have been teaching at the electronics department. So I have quite a bit of knowledge about this area. So uh, we will start from these aspects first. First of all, a very basic introduction to image processing and early vision. And we will look at how sampling is done, interpolation, so-called point operations, and how filtering is done. Um, I will briefly mention this, but I will not talk too much about these things, edge detection, feature extraction, and optical flows. Um, so this part is for me to introduce you to this general basic image processing operation. Now these operations, except these things like feature extraction and optic flow, are available in popular photo processing software also, like Photoshop, GIMP, and so on. As a second part, I will talk about 3D vision. This is very important for robotics, which you are following in this course. We will talk about how you can take a camera and calibrate it. That means you can obtain the internal parameters of the camera and, of course, in external parameters also if you require. And then we will look at how two cameras are related to each other. As human beings, you know that we have two eyes like that. When you have more than one camera, you have the some kind of a 3D sensation. So how to get that, and then we'll talk about the conventional ways of doing 3D reconstruction, structure for motion, and so on. Then dense reconstruction, briefly about these things, not too much, and then I will prepare some material on SLAM also, simultaneous localization map building, not actually about SLAM, how vision is used in SLAM. And then I want to talk about briefly the deep learning for vision part, where we can briefly study about the linear classifier, image classification networks, mainly using the convolutional neural networks. And briefly about object detection and so on, because in robotics now it is very important when you have self-driving and so on. Uh, you have to detect pedestrians, cars, and other vehicles, and so on, how these kind of things are done. There we will study the so-called two-stage detectors and the single-stage detectors. So I think there is this very famous detector called YOLO. We will study that also. Uh, Now, depending on the time that we have, I have been given three lectures. Time that we have, I will talk about the little bit of new things that are happening. CLIP, SAM, and VLM. These are not actually very new, but some of these things we will talk about. Yeah. So whenever you have a question, do not hesitate to ask. You can type the question in the chat box, or you can turn on the mic and speak at any time. So here is a person who claims that he knows a bit of computer vision, so you can understand this very important area uh, through this. Yeah. Okay. Any questions up to now? All right. I hope it is okay. Let's move on. So there will be quizzes. So I have put best 2 out of 3, but there will be more quizzes. But these quizzes are very easy. Okay. When you this to encourage you to participate and be engaged with the lecture. So not to examine you or something. So today also there will be 2 quizzes, and we can do that collaboratively. And they are very easy quizzes. And then I plan to give you 2 assignments. Of course, these all these assignments can be done using large language models. If you have ChatGPT or Claude, you can get them done. But I encourage you to do it on your own so that you can learn this basic image processing operations and a little bit of computer vision. Then I will maybe perhaps Professor Buddhika will allow me to include a question in the final exam. Let's see, depending on his decision. Okay, so let's briefly talk about the early vision and what are the techniques that are important in very classical kind of early vision. And then we will move on to other techniques. For example, in this case, you can see some image. It's a famous image actually. So now it is of low resolution. You can see. Now we want to do make a high resolution image. So zoom the image. So when you want to do that, we have to think about the sampling and interpolation, right? So Fourier analysis is also a part of this, but we will not have study to discuss about that too much. Um, then we will talk about the second topic, that is linear filtering. So you can see this image of the giraffe skin, and you are filtering it with some filter that looks like this image. So we will study all these things. How do you represent these filters using things like images? So this is the purpose of this, is to detect the edges. So you can see here there is an edge, right? A black to white transition, or white to black transition. Here there is an edge. Here there is an edge. So in this output image, you can see that those edges have been emphasized. So we will understand how to do that. That is done through the filtering operation or the so-called convolution operation. We will understand how to do that. So I thought of not talking too much about this feature extraction, but the essentials that you need for robot navigation about feature extraction, I will talk about. That means you can see here the corners have been detected. This is this famous Oxford corridor of the so-called, I think, VGG group, I think, must have created this image. So these are corners, and here you can see blob-like structures have been detected at multiple scales, right, in the sunflower field. So irrespective of the size of this circle, they have been detected. This is called blob detection, and like that, people extract features and people understand how to match these features. That's how when a robot is navigating, it is able to match features across the frames that the camera receives. Then after that, you are able to get the 3D sensation of the environment. So this one is very important in simultaneous localization map building when you navigate robots. And these are available in ROS and ROS2, I think, although I'm not a user of those. Also, this is the basis for new large-scale 3D reconstruction algorithms also. So, for example, the best paper award for the 2025 CVPR conference, this is the most highly ranked conference. The best paper award went to so-called VGGT. This visual geometry groups, some paper that does 3D reconstruction, depth recovery, camera pose detection, and all sorts of things. So you can see it is a very important field uh, for robot navigation and so on. And it is using cameras. And also there's one more thing that is when LiDARs are used. When LiDARs are used, you know that there's a point cloud coming into the camera. And using this point cloud, you should be able to detect objects in the point cloud. That means whether there's a pedestrian, whether there is a car, whether there's a bus, and whether there is this, trees, the buildings, and so on. So obstacles like these are also possible, and it's not a part of this course about point cloud work, but it is an important field in the area. Yeah. Then optic flows means across two frames. Now think about a movie or something, okay? The frame number one, frame number two. You know that there are 30 frames per second, right, in a regular video. And you can see these pixels have moved this way, right? So those are represented by these slight small cyan arrows, and these two characters have moved that way, represented by little red arrows. So this is called optic flows. That means computing the motion of each pixel, um, okay, important pixels in this case, it's called optic flows. Uh, so we will not study about that, but this is again a part of image processing and early vision. Yes. Do you have any questions about this? So don't hesitate to type a question in the chat. All right. Okay, let's move forward then. Okay. Then in a regular computer vision course, when I have 14 lectures, I do fitting and alignment also. So this is the second part of computer vision. What that means is you have detected edges and so on. So today I will show you how to detect edges. That is for sure. Hopefully today. And then for those edges, how do you fit lines? You can see the longer lines have been fitted in this case, right? So this one is called alignment, how to align uh, points to a line. So then here you can see there is no billboard here, and they have been able to put a billboard in a perspectively correct manner. When you look at it, you know it is correct, right? For example, these characters are getting smaller and smaller as you move further away from the point of view or the camera center. So this is perspectively correct, and that has been put using some computer vision algorithm. That is not an actual image. So, for example, you have seen prickle grounds are there. There's nothing drawn on the grass, but when the match is going, they display some advertisement on the grass. Like it's like popping up. Oh, it is like on the grass. So those things are done automatically using these kind of techniques. This is a part of image alignment, and you have a technique called image stitching by computing so-called homographies. So this is the alignment part, but we will not cover that in this class. Okay. Then we have to look at the image formation. We have to look at this in this class. That means understanding the projection model, how a 3D scene gets mapped to an image. And this is, of course, depending on the cameras. And we will briefly look at camera optics. I don't know too much about this, but I will try to say. Light and shading is also a part of image formation, but we will not look at it. Color also is very important, but we will not discuss about color in this course. Yeah. Then comes the 3D vision. This we will discuss the camera calibration. So you can see in this case, they are keeping a checkerboard pattern and the camera is here and they are extracting the internal parameters of the camera by using this checkerboard pattern and many images made of this checkerboard pattern. Then the two-wave geometry is when two cameras are looking at the same scene and then how these images are related. So there we will study something called so-called epipolar lines. For example, if you take one point here, that will be on the corresponding epipolar line. This is the uh, two-wave geometry. And then after that, we want to understand what structure from motion means. That means the reconstructing the 3D scene in 3D, as well as getting the camera positions. So we will not have time to look at stereo or these so-called nerve-like reconstruction methods. This appeared in 2020, I think 2020 or so. But if we go have time for the additional topics, we will look at this nerve technique also. This is the paper I mentioned, the best paper of in CPR 2025 called VGGT, which I don't know the exact visual geometric group transform or something maybe. So there you can see they obtain that many images and then they have neural networks. They can reconstruct the scene in 3D. Also, they can have the depth map. You can see the close by things have been given the color blue, and the far away things have been given the color yellow. And then you can see features have been matched across the images, and then a 3D reconstruction has been obtained. And in 3D reconstruction, we cannot know it just by looking at this, but if we are given the 3D reconstruction, we should be able to rotate it and see. And then you can see they have recovered the position and orientation of the camera. So this is the kind of thing that we mean when we say 3D reconstruction. But this 3D reconstruction being into 2025 has been done using deep learning techniques. What we will learn will be based on classical techniques. And then when we study deep learning parts, we can maybe think about it, but I don't think that we will have time to discuss these things in detail. Yeah. This is called 3D vision. And then another part of vision is segmentation, but I will not do that. This is very important for example, medical image segmentation. You can see here they are segmenting cells. This is called this very famous paper called SAM2 by Facebook. And you can see the football has been segmented across frames, and also the shoe, and then and so on and so forth. I think you saw here. I will show that again. You can see the things will be getting segmented, right? And they can generate 3D thing also. That is not a part of segmentation. Okay, so I'll briefly mention what segmentation is, although we are not covering in this course. Uh, if you input an image to a segmenter, what we will get is a labeled image. But that means is for the wall area, it will assign one label signified by a color. We just put a color so that people can understand. For the chair area, you put one color, and so on. So this is called segmentation into multiple segments. So, but there is binary segmentation also. So this one called semantic segmentation. Semantic means it's connected to the way the human beings would interpret. And then in here, it's binary segmentation. You can see an image has been inputted here, a llama image, and it runs through the segmenter, and you get a binary mask, foreground versus background mask. This is important if you want to extract a character out of a photo and paste it somewhere. You know that in your WhatsApp and other social media, it is possible for you to create emojis using these character stickers, using these characters, and these are done using segmentation technique. That's why these social media companies are quite interested in segmentation also. So any questions up now? So I'll be very happy if you can ask a question. Otherwise, I will also feel bored. Any question, you can type some question, then very good. Okay, then we will move forward. Okay, so then came the deep learning for vision that also I will do in this course. The 3 lectures I have been given. The one of the early networks is the network by Professor Jan LeCun. So this is in 1990. So he had this problem of recognizing the characters in checks, handwritten checks. So this one is for recognizing handwritten digits. So you can see for I think character recognition also he had a similar effect. You can see the letter A here, and then finally, actually this was digits. Finally, an output of 10 nodes. So 10 means 10 digits. So to recognize from detect from 0 to 1, 2, 3 up until 9. So if number 2 is high, number 2 is digital, the second node of this one will become high, and so on. So this is called a convolutional neural network, one of the very early networks that were introduced by Professor Jan LeCun. So maybe perhaps you know that these three people obtained the 19 Turing Prize. I will show that so that it's we'll see some context. Uh, so Turing Prize, you can see that yeah, their image here. Professor Yoshua Bengio, Jeffrey Hinton, and Jan LeCun won the Turing Prize. I'm happy to say that my students have taken pictures with Professor Benju and Professor Jan LeCun, with Professor Jeffrey Hinton. But finally, you know that in 2024, I think, Professor Hinton won the Nobel Prize. Nobel Prize of Physics. So it is that important, this contribution to deep learning. A question, sir, can you share the lecture material slides after the lecture? Yeah. Okay. So thank you for asking that question. It's very important. So I have put them on the Moodle. So under this week, May 17th to 23rd. So this is the introduction slide that I'm following now. I thought that you're very familiar with this kind of thing. I'm sorry about that. And then I will do another part today, the point operation, and then some other instructions also. And then this is the first quiz. Quiz is also there. So some of you can actually start doing the quiz, but we will do this quiz mainly together. Yeah. Okay. Yeah. Thank you very much. So a lot of things are there to be done. So I hope you are intrigued by looking at those images. So this is very, very important things to learn right now. And now these neural network things were there, but the researchers were not given the due recognition those days. Um, so Professor Jan LeCun and maybe you have taken his courses, and the other two people that we talked about. These people kept on working on neural networks, and people did not give them due recognition because people thought that the neural networks were unprincipled. Actually, I was also uh, not interested in neural networks because I also thought that they are unprincipled. But a revolution happened in 2012. This 2012 revolution was by this neuroscience paper called AlexNet. AlexNet paper was written by Alex and others. So ImageNet classification with deep convolutional neural network. So they had convolutional neural network. We will study convolutional neural networks in my part of the course. And you can see they had two GPU cards. So to run these networks, deep learning networks, you need the GPU card, and they had two GPU cards. One part of the network was on the top card and the other was on the bottom card. So this is the exact picture that was there in that very famous paper. This is one of the greatest papers of all, most used papers of all time. Uh, so who are the authors of this paper? So I'll show you a picture of that again also. So AlexNet authors. So these are the AlexNet authors. So you can see this Alex Krzyzewski, the first author of the paper, and he's you can see Ilya Sutskever, and this is Jeffrey Hinton, Professor Jeffrey Hinton. So he won the Nobel Prize. So do you know about what Ilya Sutskever? Ilya Sutskever is the person who I think gave leadership to OpenAI, ChatGPT is from that. So I think he was the brain behind this, although I cannot say that in a confirmed manner. A lot of people know that. So Alex Krzyzewski. So you can see the contributions that these people have made. So if you take these papers, for example, if you go to Google Scholar and search for this paper, ImageNet classification of, yeah, this one. So you can see that paper has been cited 155,000 times. So this is more than the DNA paper, citation the DNA paper has received. And even this paper, deep residual networks image recognition by Kai-Ming He and others. How many times has that been cited? 325,000 times. So this is this is much more higher than the total number of citations the whole University of Morocco has. So you can see just that one paper by Kai-Ming. So these are great contributions that have shaped the way the world thinks now. This is that paper. So Kai-Ming has another one called R. Yeah, you can see the great contributions that these people have made to this world. The great names, great people. Okay. Yes. Okay. So you see, you must be intrigued to study about this. So I will do my best to teach you some of these things. So. Kai-Ming is deep residual network. So This network had just 8 layers. AlexNet is an 8-layer network. 8-layer network. So this one, I think, went up to 152 layers. So you can see that Chaim in his paper showed us how to have many more layers in these neural networks. So this number of layers is very important so that you can get a global perspective uh, of the image that we are considering. This deepening this network, so therefore gave a great contribution. And then in 2017 also one more extremely great paper came. This is by Google, Vaswani and others. In 2017, attention is all you need. So they introduced the so-called transformers in this one. So you are following the electrical engineering program. For you, the transformer means, I think, the thing that is fixed to give convert power, convert voltage from 11,000 to 230 and so on. Uh, that is one meaning of the transformer. There's another meaning of the transformer, that is this Optimus Prime Bumblebee, the transformer movies transformer. But the third meaning is this so-called transformer that was introduced in this famous paper called "Attention is All You Need." So we can see how many citations that paper has received. That's also one of the revolutionizing papers. Attention is all you need. Attention is all you need paper cited by 247,000 people. So you can see how important these papers are. Based on this, attention is all you need. You know that this is by Google. Google came up with BART. We will briefly look at BERT. We briefly look at BERT today for language generation, and then ChatGPT, the OpenAI, they benefited from this kind of knowledge, and then they had their own contributions, and all these large language models came into the world. Starting with this 2017 contribution, you can see not so long ago, right? Not so long ago. So, any questions about these papers and what people have done or anything else? Okay, then we can move forward. Then deep learning, when you consider deep learning for vision, so we want to briefly talk about so-called fast RCNN, that is an object detector. Can you explain a bit about image generation using diffusion model? Yes, yeah, that's an important question. I have a little slide for that. I will explain that when the slide comes. So toward real-time object detection using regression region proposal networks, this is for object detection. That means drawing a bounding box around the car, bus, and so on. So this is a topic that I want to cover in this class. Um, Object detection. Then one of the very famous object detectors is YOLO, and this is the 2016 a picture of 2016 paper. So you can see they have been able to draw these bounding boxes with a probability indicating how certain that detection is. And then after that, YOLO different versions came. Now you have YOLO 26 that came into the world in 2026, and these are now done by a company called Ultralytics. Then this is so important uh, for object detection. For example, last year, one of our project groups came up with a device. This speed measuring devices. Maybe you have seen that policemen have those speed guns. Their speed gun, what they did, can detect the license plate, keep a record of the license plate, and also take a picture. So you can see they have to be able to detect objects for that motorcycle, car, bus, and so on, and then detect the license plate and recognize the characters also. They all did this in an FPGA, field programmable gate array, not on computers. For them to be able to do that, they took some version of YOLO and coded that in a manner that is friendly to be run in the FPGA, field programmable gate array. So these are extremely important actually. So now that is YOLO. So for all these tasks, there came another very revolutionary architecture called Vision Transformer. An image is worth 16 by 16 words is the title of this paper. So here that was applying the transformer concept that is in 2017. For that 2017 paper was for words, and this is for images. So how to do image classification using transformers. and then other things using transformers. So this is the paper that did that vision transformers. Now, invariably, any vision task is done using vision transformers, unless they are very small or simple tasks. Yeah. Then this is the paper that you're asking about, the Rombach's famous paper. This is called stable diffusion. Why it is from that company called stable diffusion? There's nothing stable about stable diffusion, I think. Mm, I will talk about image generation in a slightly more simpler manner, but this is a picture from that paper. So in that paper, the idea is this. Now you can take an image and keep on adding noise to that until you get noise. Yeah. Keep on adding noise to it until you get noise. So this is the noise addition process. But while doing that, remember we have all these images, totally correct image, little bit noisy image, little more bit noisy image, and finally total noise. So you can see each of these adjacent images we can have. So what we want to do is to learn the reverse process. That means how to remove a little bit of noise. Yeah. If you learn how to remove a little bit of noise, and finally, if you keep on removing a little bit of noise one at a time, finally you end up with an image. You started with noise and kept on removing noise. Finally, you end up with an image, and that is done by this network. So you can see to that network, you can get the give the lot many things. So you can give a textual prompt here. You can see here there's textual prompt, some representation, images, and semantic map, so-called semantic map. All these things can be given to that, and based on that, they generate images. So this is the stable diffusion, but the latest method of doing image generation is not diffusion. Now there's a thing called flow matching. People are using flow matching for image and video generation. Okay. So now from this part, I want to briefly talk about image processing and computer vision that I've done, and then I will introduce AI, ML, deep learning, and AI where all these things fit. What is machine learning, neural networks, and deep learning, and convolutional neural networks where they fit in the large picture, and attention and transformers where they fit. I will briefly talk about, and then we will introduce a little bit of generative AI, how images are generated, how text is generated. I think I'll answer Sanat Tilakaratna's question in that part. And then I will show some projects done by our department. I'm always happy to do that. So a little bit of, maybe you can say it is advertising. Okay, so let's go through this. Before that, if you have a question, you can please ask. Okay, what is image processing? Now, image processing is taking an image and sending that to the so-called image processing algorithm and getting a modified image. In digital image processing, we manipulate digital images to produce another digital image, which is an enhanced version of the original image. So you can see the input is an image, see, and the output is also an image. Okay, it is modified, but it is an image. It is not like text output. Like if you take ChatGPT and so on, your output is text usually, right? You ask a question, output is text. You upload an image and you ask a question, output is text. But here, input is an image, output is an image. The main example for this is uh, Photoshop. You can do processing on images using Photoshop. You can see input is an image, output is also an image. So in digital image processing, we manipulate digital images to produce another digital image, which is an enhanced version of the original image. This we call image processing. And examples are blurring, noise filtering, color enhancement, segmentation. Some people call it image processing, but I think it's slightly more complicated than image processing. So here you can see I have given examples of a noisy image and the processed version of that. So here you can see the noisy image, a little bit of noise here, and Gaussian filtered image here, for example. So Gaussian filtering is and a smoothing operation. It reduces noise. So you can already see if you open the slides and see for yourself, you can see the noise has been removed. This is called salt and pepper noise. Yeah, it is like sprinkling salt and pepper on your plate. So you can see very high intensity pixels and very low intensity pixels, and producing a clean image like that by removing those median filter ring noise is also an image processing operation. It is not a computer vision operation. Any questions up to now? Yes. So now that was image processing. So what is computer vision? In computer vision, you give images, text, or images, text, or video to this computer vision system. What you get is a decision. What you get is a decision like where the human beings are. Can you see they have drawn boxes and colored the pixels? So that is a decision, right? It's not an image output, it's a decision. So for example, if you do face detection, it's an early face detection output. You can see it's drawing the uh, rectangles around the faces of human beings. So this corner and that corner. These are four numbers. And deciding that number is the decision, that belongs to computer vision. So this image, I think I created, not I think, I created using Google Whisk for you to look at it and be happy. So you can see the prompt that I have used and the great image that has been generated. So you can have a look at it and enjoy yourself a little. All right. This is the prompt I gave and it generated a beautiful image. Okay. Yes. So now, where does all these things fit in this larger umbrella of artificial intelligence? That's what I want to talk about in this slide. So you can see AI. What is AI? We want to see what is ML, what is NN, neural networks, what is deep learning, and what is and generative AI. So deep learning is a machine learning advancement that allows the system to automatically discover or learn representations. So what this means is this: if you see a car, we represented that using a vector of numbers, maybe 1028 dimensional vector of numbers. So this representation, so what is the right representation? How do you do that representation? When you represent, do two objects like car and the bus remain far apart from each other, right? I mean, they are not the same. So that representation should be different for a car from a bus. So this representing rightly is the purpose of uh, deep learning using a stack of multiple deep layers or neurons or a neural network using data. So you can see a lot of information is packed in this. One is what representation learning is. We studied that using a stack of multiple layers. So you can see these so-called neural networks, they are little computational units and they are arranged into layers. And when you have more than 8 layers, we call it deep learning, more than 8 layers. Okay, I hope that is clear to you. All right, so now this is how it is there. So overall thing is artificial intelligence. So artificial intelligence means making machines that work and think like human beings, that behave and think like human beings. This is a very hard thing to do. It's not been achieved. Then machine learning is learning from data or learning from experience. So here also you can see the data term has been mentioned. And neural networks are a technique of machine learning, learning from data. So it stands within the umbrella of machine learning. And then the deep neural networks, of course, You can see deep neural networks are so-called neural networks that have more than 8 layers. Why do we say eight? Because AlexNet, which was considered to be a deep network, had 8 layers. So if you have more than 8 layers, you call it a deep neural network. If you use those neural network technologies. Then finally, generative AI is also, it can be outside this set of circles also, but it is usually, we can draw it inside, and you can see it is a part of deep neural networks. So that's what we call by deep learning. So deep learning is when you have in your network has more than 8 layers. So any questions about this overall diagram? Yes. All right. So now the next question is, what is the difference between these so-called classical techniques that we are going to study first and this new paradigm of deep learning? So in the classical networks, the way you represent things, remember the representation learning, represent things is using a feature extractor that is usually hand coded. This representation is here. You have some operation that runs on the network and gives you a representation of the image using using numbers. And then on top of that, you have a classifier. This classifier, for example, will say for cats C, and for dogs it may say G, right? So you can see the labels are coming out of that, the cat label and the dog label and so on. If those labels are correct in comparison with the ground truth or the actual labels that people have given, we are happy. Otherwise, we are not happy. Then we are making a loss. So based on that loss, we can derive an error signal, and that using that error signal, we change the parameters of the classifier. We don't change the feature extractor. We will only change the classifier. See, this one is what is being trained or changed. But when you come to the neural networks paradigm, you have the neural network or CN or the transformer, and there you can see the labeling part and training part are there, and then you can see from the loss. Any questions about this? Okay, so now
So
you can
usually,
ask, yes,
what is the top one and the bottom one, sir?
these two things, this one and this
Yes,
one. Ah,
yes, sir.
yes, yes, yeah. Thank you. I did not explain that. This is the classical way of doing image processing, object detection, and so on. Classical classical way of classifying between, for example, cats and dogs. So this image is a cat image. No? So this image we have to say cat. For this image we can say dog. So classical paradigm of image classification. We can say, okay, of course it is applicable to object detection and so on also. And this one is the new paradigm, that is a neural networks paradigm of image classification. So this, you can see the feature extract is no longer there. The feature extract and the classifier have been combined into one neural network here. That combination is so important. So now you can see the features extracted are supportive of being classified. Yeah, supportive of getting the right classification label for the input image. So that's the value of combining this classifier and the feature extractor. So therefore, the representation of the image is not exactly at once visible to us. It is inside the neural network being computed. Sorry about that. Yeah. Thank you very much for that question. I'm encouraged. So, what are the other questions that you have? Okay. Now you can ask, why now? Now these things people could have done earlier also, right? Why did this suddenly deep learning things did suddenly come? The reason, there are two reasons. First reason is the people understood that research translates into industry. So, for example, if you take ChatGPT, you understand that the people have been doing this kind of language generation for a long time. But now companies can make money out of it. Money means large amounts of money out of that. So research translates into industrial value. Research knowledge is the power. So people understood that, and people were able to apply that and start getting economic benefit. So that's why deep learning became extremely popular and extremely widespread. And then the computational power became available. See, in extremely good processors like Intel i9, these are external processors, and you have the server gate processors, also Xeon processors, and so on. These processors are great processors. They are good at doing complicated calculations, but not a massive number of uh, computations at the same time. At the same time, but if you take a computer graphics card, these are advanced cards, they can do small computations massively parallelly. Large number of them parallelly, these cards can do. So, for example, NVIDIA RTX 5090 is a gaming card. Although it's a gaming card, uh, these graphics, you call them VGA cards, right? VGA cards. These cards are these gaming cards, but they are very powerful. They can be used for computation. But professionally, you don't use gaming cards. You have this NVIDIA B200 and so on. These are extremely powerful. These are big, okay? These powerful cards, and they are very expensive. Only large companies can buy them. Even if you have money to buy, they will not release those cards to you. Yeah. That's one reason. The other reason is the computational frameworks became available, like TensorFlow by Google, PyTorch by Meta, and that's also. And then these platforms, we could have these representations and get them working on circuits or FPGAs. So this is a summary of the reasons why deep learning is prevalent now. Any questions about this? Let's briefly move to the success stories. See, there are many success stories of computer vision and deep learning and so on. One of the first success stories is the self-driving cars. So, think Waymo's car, it has a number of cameras as well as it has a LiDAR. LiDAR means you send the laser, and the detection and ranging can be done based on that signal. So those are one uh, rely on multiple sensors, but Tesla, as I have heard, they only use cameras to detect things, to detect what? Detect the pedestrians, detect the cars, and detect the drivable area. Can the car drive on this area? uh, and for all sorts of things, they use computer vision, Tesla cars. Then, of course, they are done using these kind of deep networks. Then the uh, chat engines. These are success stories, and now especially for programming, they have become extremely successful. Um, OpenAI, ChatGPT, Google Gemini, and Claude's uh, Opus, and so on, other versions of their large language models that are helpful for coding and so on. And then large scale face recognition is successful. And you know that your phones have assistants like, for example, Apple Siri, and Samsung also Bixby or something assistants are there. Then this is the coding Copilot. Using that, you can code faster and so on. So these are some such Amazon's personalization. That means if you buy something, the next time it will say that the people who bought this also bought this, and then show you advertisements that you will like based on your choices. So, yeah. Any other questions about this? Like, Okay, then. So here I'm giving the examples and as well as the key technologies. So major areas of application of AI. So if you take computer in the computer vision area, self-driving car, and for example, movie production. These are also done using computer vision techniques. The main technologies are CNNs, convolution neural networks, and now transformers, defect detection, volume adaptation, VR displaying, self-driving. All these things are computer vision applications of the area AI. So I will show you how Avatar was produced. So some of you may have seen this. I'm sorry about if so.
Yardley, experience the legacy of luxury.
I went to the studio and I said, let's not just do another movie. Let's swing for the fences.
I think what people are in store for is Avatar but times 100. It takes it to a whole other place.
I've never seen anything like this in a movie. It picks up where it left off, and he just...
It was wild. My eyes were glued to the screen, and I can't wait for people to see it. The world is bigger. The stakes are higher. This is our home! I was always looking at everything in wonder.
What Jim is trying to create is very truthful, very emotional and grounded tales.
I need you to be strong.
A family trying to survive.
Strong-hearted. It's really got this level of magic and crazy. It takes years to make these movies. Like, there's nothing like this.
It was the experience of the first movie, but on steroids.
There are different ways to make films that have CG characters. What we're interested in with performance capture is the totality of the performance. Physical, emotional, facial, the eyes, everything. The actor creates the emotion. The actor creates the moment. It's our job to make sure that everything the actor did is preserved in their CG character.
You are very hard on them.
I'm the father. It's my job.
Everything that Jake Sully as a Na'vi does, Sam has done.
I thought we lost him.
You can capture the emotion, you can capture the subtleties, the nuances of the movements, you can capture the eye, you can capture the tics, everything. Capture it all.
Okay, that's enough. You can watch it at home. So you can see that's one of the great applications of computer vision, movie production. Yeah, so these are things. And then in natural language processing, we have Google search, Google's Bard now, Google Gemini, and OpenAI, ChatGPT, Meta's Llama, Llama 4, and so on. They are now, like a little bit old. And the main technique that drives those things is the transformer, and then public chatbot negotiators, agents, and so on. These are the example use cases. And then data analytics. In data analytics, you can see Amazon's product recommendation system, YouTube's video recommendation system, quantitative finance models for the improvement of hedge fund or something. These are all data analytics work. So machine learning, big data, NLP, cloud visualization. These are the techniques that are important in that context. And then recommender systems, customer proofing, and business analytics. All these things are example use cases. Yeah. Okay, so now a little bit of about learning paradigms. First of all, supervised learning. In supervised learning, we learn from labeled examples, like a student trying to answer, studying with answers provided. So it needs pre-labeled data like flashcards. For example, you have a folder called cats folder. You have a folder called dogs folder. You have a folder called deer folder. In all these cat images are there in the cats folder, dog images are in the dog folder. So you can see they have been human labeled. They have been human labeled. So if we have time, we will do an exercise like that of adapting an existing network to recognize characters. Yeah. You can see in supervised training paradigm, you learn from labeled examples. So now, for example, like that, we have an apple as well as a label apple. We have banana image as well as a label banana. We have strawberry image and the label strawberry. We have a pineapple image and the label pineapple. So we sent that through the supervised learner, and then it will predict something. For the if you send the apple, it may predict banana. So that's wrong. If it is true, it's good. If it is wrong, it makes an error. So we change the parameters of the supervised learner so that these errors are minimized. We call them losses so that the loss is minimized. Yeah, I hope that's clear to you what supervised learning is. So don't hesitate to ask any question at any time. Um, you can either use the chat box or you can turn on the microphone and ask. Thank you. Then self-supervised learning is a very, very important paradigm now. The reason is it is not possible to label all the data possible. So many images of cats are there, right? So different types of cats. You cannot label them and finish, right? So therefore, we have to find a mechanism of not labeling, but being able to use the data. So here we use signals that are in the data itself. For example, this one, right? So if I say, I blank going to Moratuwa, right? I blank going to Moratuwa. What is the word for blank? I am going to Moratuwa, right? So you can see if we remove some words, so mask out some words from the other words, we can find what that correct word is. So if you have large amounts of text browsed from the internet, downloaded from the internet, you mask out some word, you have the correct one because you have the original sentence and you masked out a word, one or two words. That's the uh, version that you give to the network. So network is supposed to predict the correct one. If it does not predict the correct one, you know the correct one because you have the original sentences. So you didn't have to hand label. A human didn't have to hand label, but use scrape from the internet. Train on unlabeled data by creating its own supervisory signal. I hope that is clear to you. Discovering patterns by itself. Two common approaches, reconstructive and contrastive learning. So we will only look at an example of reconstruction learning. So I'm sorry, I forgot to tell in supervised learning, after you learn the supervised learner, then you give it an image like a strawberry and it will produce the label a strawberry. So this is called the testing time. So you have the training time and the testing time. So here about the supervised learning, unsupervised, self-supervised learning, you can see this is the reconstruction-based one that we are talking about. So for example, if you have seen that you have an apple image, the original image you have, you mask out some areas of the apple, right? You mask out this rectangle, you mask out that rectangle, and give the image to the network, and network should be able to reconstruct that. If it properly reconstructs, you know because you have the ground truth for the correct original image. If it makes a mistake, you can punish it therefore. If it correctly reconstructs, there's no problem. So like that. So mask out some parts of the image, mask images, and you feed that to the network. So network's task is to reconstruct the whole image, including the masked areas. If it does it right, it's good. If it does not do it right, then you have to change the parameters of our network. Yeah. Okay. Then in the testing time or the so-called fine-tuning time, we take this part of the network, and we can get the representation of the strawberry here. Why? Because now this has been trained on so many examples. Now, if you give a strawberry, it will produce the correct embedding or the vector that represents the strawberry. Then, based on using that, you apply a very small classifier on that to be able to classify between cats, dogs. Okay, in this case, apples, bananas, strawberries, and pineapple. Okay, so yeah. Any questions up to now? We will not study reinforcement learning. It is very important for robotics. I'm sure that someone is teaching you reinforcement learning. I'm not quite knowledgeable of reinforcement learning. Okay. So let's briefly see how this kind of thing is done in the supervised learning paradigm. So you can see here, we are taking an input image. Maybe this image is maybe 32 by 32. 32 by 32. So that means how many numbers are there? 32 by 32. Let me calculate. I think let me calculate. 32 times 32. Thousand 1024 dimensional vector. So if you just use the raw pixel, my D here is 1024. Each image is represented using 1024 numbers. And then you're multiplying them with some weights. These are called weights. You're multiplying with weights. So you can see if you represent W using a matrix and then X using a vector, all X's, you can have a formula like WX plus B. So there's a little bias also that's not required to be considered at this stage. We can capture that into one of those weights. So we get the sign of Wx plus B. If the sign is positive, it's some class. If the sign is negative, it's another class. But you can do better than that. So, but right now, I hope you understand the concept of the perceptron. So this perceptron thing proved out to be not so robust due to some reason, which I will describe to you later. So therefore, they added the multiple layers called hidden layers also. And then sorry about that. Getting the pen to the correct location is sometimes a problem. So you add these layers with non-linearities. So we study what those non-linearities are later, and then it produces the usually the correct output. And then this is the variability of the perceptron that was. I will show you the Navy article that described this. But what people discovered is that perceptron is a linear classifier. What that means is this. Now assume that in this picture, you would classify between orange rectangles and red circles. So you do the classification by drawing a line. That's why it's called linear. So you can only separate these two classes by drawing a line. That is a problem. So in a 3D space, by having a plane. So, but if you use the multi-layer perceptron, you can have boundaries like this. You can have curvy boundaries like that. So here you can see it is made, the network is making some errors, right? This is an error. This is an error. They are called training errors because that has happened during training time, training errors. So here you can see, because we can make the more powerful curve, more powerful classifier that can curve, so that can represent an arbitrary nonlinear boundary. Nonlinear boundary, not arbitrary, nonlinear boundary. Yeah. So now, at least in the training set, there are no misclassified examples. But giving so much power to the network is also bad. It will perform very well on training time, but during testing time, it will drastically fail. So that's why the uh, multi-layer perceptron concept is so important. And especially the nonlinearity. Nonlinear concept is also very, very important. Okay, here is that famous article that so-called introduced the perceptron. It's a 1958 New York Times article. I will draw your attention to some important things. Washington, the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, respond itself, and be continuous in existence. So what a great expectation, right? So now we know that we have the read-write machine, but walking and talking machines also we can do, seeing everything, and yeah, these are slightly challenging problems still. The embryo, the Weather Bureau's 2,000,704 computer learned a differentiate between right and left after 50 algorithms. 50, I'm sorry, what I'm saying, 2 million the algorithms for the embryo, the Weather Bureau's 2,700,000 for computer learned to differentiate between right and left after 50 attempts in the Navy's demonstration for newsmen. So, but this is not the important part. The next one is the important part. The service said it would use this principle to build the first of its perceptron thinking machine that it will be able to read and write. It is expected to be finished in about a year at a cost of $100,000. So now you can see after this 1958, about 70 years have passed and billions of dollars have been spent, but now we have reading and writing machines. So this is done by a person called Dr. Rosenblatt. Yeah, so this is some history. Okay, so let's look at briefly some image classification also before in the introduction itself. This is a very simple linear classifier. Linear means what? It is the equation is like that of a line. So what is the equation of a line? So we know that the equation of a line is y equals mx plus c, right? That's in 1D. Y equals mx plus c. So you can see that this is exactly like that, right? Mx plus c. So it can only represent a linear surface. That means a line in this x1, x2, 2D space, in the plane in the 3D space, hyperplane in multi-dimensions. That's what it can represent. So this is why it's called linear classifier. So here, let's take a linear classifier. The thing about linear classifier is you take the image and multiply it by the weight. So assume that this ugly, very ugly looking cat, I don't know why they picked this cat, very ugly, is represented using 4 numbers. But we know that a cat of this size will be represented by a larger number of numbers. For example, in the ImageNet, they have color 224 by 224 images. But in this case, we are taking 4 numbers to represent. So these 4 numbers correspond to our x's. So for each image, and then there is a row. This is the cat row. This is the dog row. This is the sheep row in the weights matrix. You take this matrix vector multiplication. You take this 0.2 and multiply 56. This minus 0.5 multiplied by 231. This is 0.1 multiplied by 24. and this is 2 multiplied by this last 2. And then finally a number is added 1.1, and then you get the score minus 96.8. This is the cat score. And then in the second row, you have the dog score. In the third row, you have the sheep score. So as it stands, which one is the largest? Now, can you type it so that I know that you are able to follow what I'm saying? As seen in the slide, what is the class of the image? What is the class of the image? So please write cat, dog, or S. Only these 3 letters. Can some people type the answer, please? So please type CDOS to show this cat, dog, or sheep. Which one is the largest? Some people are typing. Thank you very much. And the answer is correct. Who else? Yeah, correct. Type correct. I'm using type correct. Ishan Marasingha type. The class is D dog because the dog score is, yeah, correct. Okay, thank you very much for your responses. We will move forward. So you are correct. The class is dog. Why is the class dog? Because this dog score is high. So why is the dog score high? We expect the cat score to be high, right? The dog score is high because this thing has not been trained yet. So when we feed multiple cat images, multiple dog images, multiple sheep images, it will make mistakes or not make mistakes. If it makes mistakes, we will correct the weights. If it does not make a mistake, also we correct. We can understand that later why. This is the call the training the classifier. So one amazing thing happened, that is this after training the classifier, if you take the cat row and show it as an image, that means you take this one, okay, you will have more than 4 numbers, okay, in reality, and show it as an image, it looked like some blurry cat. If you take the car image, car row, it will look like a blurry car. If you take the horse, it will look like a horse facing left and facing right. What's the reason? In the existing horse images, there were horses facing left and facing right. So the classifier learned to handle both these things. So isn't that amazing? So this is a linear classifier. Actually, you can code it in maybe 10, 20 lines in Python. Maybe we will not do that. Yeah. Let's see. Depending on the time, we can do that. So that is the linear classifier. So you know that the perceptron is this, and then people found problems in the perceptron. But then after that, people went with the convolutional neural network, so CNN. So there is a video link to the slide. So actually, you can play it on your own. But right now, I will not do it too much because it will take time. So the actual operation of the neural network is shown here. So I have a link here so that you can go and watch. For example, when the person clicks ladybug or pizza, you can see the probability of that becomes high. So that means as the input image, you give the ladybug pits and so on. So then the corresponding classes probability goes up. So in this animation, you can see how externally, internally also these nodes learn how to do that, and they can expand this and show you the actual learning process. Okay, you can see some of these things happening, but this so-called convolution is running. We will briefly study about those things in the class, but right now I will not spend too much time. You can do it on your own. So this is now that you can see that the previous one, the convolution, is the operation that gave rise to these convolutional neural networks, and how they very well worked. And then in 2017, I said that transformers were introduced. In the transformers, the main thing was the attention. So I will briefly explain you what attention means. In this example, now take this sentence, for example. The animal didn't cross the street because it was too tired. I'm asking you, what does it refer to? What does the word it refer to? You will obviously say it refers to the word animal. So therefore, we have shown this line's thickness, the thing, and using which it attends to the animal. It has some attention to the street, some attention to it itself, some attention to the full stop, and some attention to the. But you can see the highest strength is for the animal. So this is what we call the attention. You take a word and see how it attends to all other words. Take the next word and see how it attends to all other words. So you by using this, you can create a so-called language model. Also this concept of attention that came with the transformers was replicated, applied in computer vision also in the very famous 2021 Dostoevsky paper called An Image is Worth 16 by 16 Words, so-called VIT, for the vision transformer paper. So I hope you understand what attention means in a very shallow perspective, but we can code them and see also, depending on the time that we have. So, all right. Okay, so then person asked about the generative models. So thank you for that question. So here is the, in my opinion, the correct interpretation of generative models. Okay, now take for example, z-score. So you know all about the z-score. That is a normal distribution. So if you take the z-score, the mean is somewhere in this probability density function. The mean mu is somewhere, right? This is the mean mu. In that has the highest probability. Can you see that? Highest probability. Away from the mean, probability is decreasing. So now if you sample a person or a student from this z-score distribution, generally you will get a student with the mean score. Do you agree? Because it is the highest probability. If you generally take a student, he will have an z-score close to the mean. In this case, the mean is 0, okay, in z-score. So if we sample from something from that, you will get a student with the z-score maybe 0.3, 0.10, minus 0.1, like that, close to the mean, because that has the highest probability. So you can see when you have the probability density function, yeah, you can generate samples that represents that probability density function. If you know the probability density function of data, you sample a point from there that will represent data, that will look like data. Okay, this is in 1D. Now let's take in 2D. So I have drawn a probability density function in 2D. You can see at the center, the density of points is high. So that density is represented by the height of the function. So if you sample, the chances are high that you'll get a number like 0.3, 0.4. The chances are highest to get a number like 0, 0, because that has the highest probability, but high probability ones have high chance of getting selected. You can see. So if you have the probability density function again, you can generate data that looks like the data set that is represented by the probability density function. So we will move further. Now let's take 32 by 32 images. Yeah. So if we have the PDF of that, the probability density function of those, that 32 by 32 dimensional one, I cannot draw that, of course. So my ability to draw finished from there. So even the next one I cannot draw. If you sample a point, and if this probability density function represents the dog distribution, you will get a dog. You will get a dog image. So in other words, assume that your probability density function is like that. So I'm just drawing something like this, okay? Because I cannot draw that in 32 by 32 dimensions. 1024 dimension, I cannot draw. So if I have, and if I sample, chances are highest that you sample from the mean area of that. If you sample like that, you will get images that you train with. That means sheep, dogs, car, and cat, and so on. But if you sample like slightly away from that one, so maybe somewhere here you sample. In this one, maybe somewhere here you sample far away. Then the probability density is very few, very small. Then you will get one. So learning the probability density function of data is generative modeling. Okay, so I answered that question. If you have more questions, you can ask. Generative models learn the underlying distribution of data for the probability density function. Once learned, they can generate new data samples that represent the training data. Okay, so if you have any question, you can ask. So if you take generative AI, so many applications are there, you know, the text generation, generative AI models like generative pre-trained transformer GPTs can generate human-like text, chatbots and content creation, example, GPT, Gemini, and image and visual generation is possible. Stable diffusion generates realistic images, and the visual content based on textual description, and flow matching, as I said, is a new way of generating these images. So in the advertising industry, entertainment industry, mid-journey, image and visual generation, and so on. Data augmentation, generative AI can generate additional data samples to augment the data for training and machine learning models, training models with less actual data, and music composition and so on. And then there are many other applications of this music composition, a system that can generate music compositions in various styles, on genres, and based on patterns learn from existing music. Important in the entertainment industry. Okay. So, so this is the one of the ways that they learned the probability density function of large amounts of text called BERT by Google. There, what they did was this masking approach. I briefly alluded to this masking approach. They take a sentence, let's stick to improvisation in this skit or something like that. So they take this one and they mask it. So this is the examples that we have done in our grade school. So teacher gave us the sentence and fill in the blanks. Exactly the same thing. So this network for each of them generates something, and here also generates that. So it generates probability numbers for each of the words in English. Maybe there are 30,000 words in English. For each of the words, it generates a probability. Hopefully, that probability would be higher for the correct word. So when you do that, this BERT becomes a so-called language model that it has learned the language. So there are other few things that you have to do. Yeah, this portion embedding, segment embeddings, token embeddings, and so on. These things are there, but we can learn about them later. After the pre-training part, you can do the fine-tuning for different kinds of things like question answering, name entity recognition, and also so other things. You can use this language model. So this is the BERT. So exercise for you. What is hidden here? It's a pair of bananas. Here's a complete picture. Pair of bananas. Thank you. Thank you for answering that. What is this? It's a polar bear, right? So because you're human beings, you are able to complete it because your brain has been trained for that. So we want to make the network also learn to complete that. Here's a difficult one. What are hidden here? Yeah, it's very difficult, but you can see that these are the hidden ones. So thank you very much. That's the correct answer. So if you learn how to generate the correct image from the mask one, you are generating a model that knows about these images. That means, although it doesn't fully learn the probability density function, it is able to generate samples that represent the data. So here's the thing about image generation. Okay. So those pictures that I showed you in the right part of the slide are exactly the pictures that are from this very famous 2022 paper called Mask Autoencoders by Cunningham and others. They took images and they masked out some patches, and they had something called an encoder and put these mask keywords back and use the decoder to decode the target. And when you have the input masked on and the target field one, you can find the difference between them and use that as a signal to train the network. This is what they did in self-supervised pre-training. And there's another one called contrastive. Here, the idea is that's also very simple, right? Idea is this. So this is the two images of the same dog. Okay, two images of the same dog. This is a different dog. Actually, this one is a golden retriever. This one is a beagle. So you have something called an encoder. Remember, in this case, our task is to represent things in the world, representation learning. This is that representation. It's a vector of numbers. I think that it's a 1024 dimensional vector. When I represent that, I want the two images of the golden retriever to be closer to each other, but the image of the beagle to be far away from those. Bring together representations of similar examples and push apart representation of differing examples. That's the thing about the contrastive learning. You learn to contrast. So this encoder learns how to represent dogs. So that's the representation learning. So contrastive learning and reconstruction or masked image learning are the two ways of doing self-supervised learning. If you ask what are the books that you want to read to enhance the knowledge in this area, Gonzalez and Woods is a great image processing book, this one, and Computer Vision, the second one by Forsyth and Pons is a great book. This is Richard Serisky's book. It's a slightly research-oriented book, but it is available online free of charge. And Milan Sonka is a good book, image processing and image analysis is both. They are both image processing and computer vision are there in that one. It's a very recent book, I think 2025 book, I think. It's available online, Foundations of Computer Vision by Toralba and others, the people from MIT. And this is a very, very useful and very good book. So if you ask what these conferences are, these are the conferences: CVPR, ICCV, Computer Vision and Pattern Recognition, International Conference of Computer Vision, ECCV, WSCV, BMBC and ICIP, journals, PAMI, IJCV, Pattern Recognition, Transactional Image Processing, Cybernetic, Computer Vision and Image Understanding, and so on. These are the good, very good conferences and journals. If you want to find out more of those, like what are the correct journals and so on for this area, you can go to Google Metrics and go to the area of computer vision and pattern recognition. So type Google Metrics here, and then you go there, and then you can see CVPR is the second conference that has H5 index. So you can see it's getting so much traction. So we go to the engineering and computer science, and then underneath that you have to go to computer vision and pattern recognition. Then you have the top ones, of course, the CVPR must be the top now. European Conference of Computer Vision, International Conference of Computer Vision, transition, so on and so forth. So in this 20 list, I think almost all are good. But if your area is robotics and so on, so you can go to robotics. So robotics and automation letters, International Conference of Robotics and Automation, Professor Buddhika has papers in this, and so on, right? Yeah. So if you go to the signal processing, yeah, so you can understand what I mean by the conference in general. Any questions about this, or are you okay? So one thing is, if you are getting started with research in this area, do not start with things that you doubt. So only start with the topmost journals or conferences. So in this one, like have the mindset, I want to solve this vision problem. What are the tools available? How to, don't think about an exam. So attend these lectures, please, and try to do a small exercise the night before. We are going to take a break now, and after the break, we will start the next lesson, and we will do some little bit of coding also, and implement a little bit of coding. So I was told that you know Python. So in Python, we will implement those. But so we use Python, OpenCV, and PyTorch. And computer vision software companies are there. These are good for if you want to be industrial vision. These ones, and camera companies. Also, I have listed these camera companies. And then camera catalogs and so on here. So here are some projects that were done at the department. So Ocean Jaising was the Island Fest. He is one of the topmost scores. I think no one can get his score now. They took all the Sri Lankan traffic signals, and they were able to achieve excellent rates. And these are published data, and the data is also available for you if you want to do any work with this. And then this is swift lane. So lane detection in Sri Lankan roads, it's not an easy thing like in other countries. So they did this work. So related to your area of interest, okay? So I'm saying. And then this is AR-based human interaction automating a robot team. You can see there are 3 robots. Yeah. This is a mobile robot. This is a mobile robot. This is a fixed robot. And we give a building plan, and using reinforcement learning, it learns how to build the building plans and starts constructing the building. So these are the bricks we have, bricks we call them. So this is done by Aditya S and others. Now I think he's a professor. He was a gold medalist also, iron based. So this is our river reconstruction project. This is an amazing magic-like project. So a lot of radiologists took part in this project, Professor Udari and so on. So yeah, we have some ultrasound scans, and we make the masks of the liver area. And then we have something called statistical shape model here. We work the parameters of the statistical shape model to produce a 3D structure by 3D reconstruction by warping the statistical shape model parameters from some numbers that we get from the segmentation. So then we can create the 3D reconstruction. Beautiful project. These are also published. So now you can do the quiz. I'll give you a little bit of time to do that, and you can take a break also. We will meet at 10:20, and I'll give you another break also later on. So we can take 2 breaks because it's a long class. So I will write here meeting at 10:20, attempt the quiz. The quiz is on the Moodle. Quiz 1 on computer vision. Very easy. You can. I think you can see. What is the goal of early vision in computer vision pipeline? Creating 3D point clouds is wrong. Extracting low-level features, edges, corners, and textures. Rendering synthetic scenes, compressing video, extracting high level. So this is the correct one, right? So like that, you can click. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz. So you can see. So this is the quiz You can look at the slides also. Please don't use ChatGPT without using ChatGPT or talking to each other. Please try to do that so that you can learn something. So I'll pause the recording and we meet in about 10 minutes time. Welcome back. In this lesson, we will look at basic and point operations. Let's understand how to represent an image in the computer, and we will understand how to do operations that affect only one point in the image or one single pixel in the image. Of course, we will apply that operation to all the pixels. Yeah. So what is a digital image? A grayscale digital image is a rectangular array of numbers which represent pixels. So each pixel can take an integer value in the range from 0 to 155 for an 8-bit image. So this is why we have 255. Now, in images, each pixel, that means each picture element or each dot is represented by an 8-bit number. So 8-bit means you have 8 binary numbers, right? 8 binary elements. So the maximum that you can get is, okay, minimum is 0, 0, 0, 0, 0, 0, 0. That corresponds to 0. The maximum that you can get is all ones. No, 1 is the maximum number that you can put, right? In a binary digit. So see, all ones. So when you put all ones, you get 255. So if you want, you can do a computation and see. This corresponds to 1, this corresponds to 2, this corresponds to 4, this corresponds to 8, and so on, right? So if you add all these things, you get 255 for an 8-bit image. That's the reason for that. If the image is color image, then there would be 3 such color arrays. I will show a picture later. The size of this array is actually the resolution of the image. For example, if you take a recent good camera, it will be like 3712 times 5568. So that means vertically there are 3712 rows, and horizontally there are 5568 columns. So giving rise to that many pixels, and we call this the resolution. We take the top left as the 0, 0 pixel and vertical axis as the y-axis. Please remember that if you make a mistake here, you will not be able to get the correct answer at exam questions. A conversion problem. So you can see here is an image. Now this image, okay, it's a representation of an image, is a 6. How many rows are there? 6, right? 6 rows in total. Yeah, can you see that 0 to 6 rows in total, and 8 columns in total. 8 columns in total. So it is a 6 by 8 image. We call it a 6 by 8 image. 6 times 8 image. This is a very, very small image. Okay, usually images are much larger. So if you take an element here, it is a 2, 3 element, right? 2, 3. So you can see it's the pixel 2, 3. The first number that we write is vertically in the vertically downward axis. Because when you represent arrays, that's the first number that you mention in a computer. This is second axis, J. So that's 3. So you can understand how you can represent a pixel. Any questions about this? Okay. We will soon do some coding also. All right, and then if you take a color image, there are 3 such planes. So you have an I-axis and you have a J-axis and you have a K-axis also, 3 such planes. The grayscale image that we considered as a 2-dimensional array or single plane, the color image has 3 such planes, 1 for blue, 1 for green, and 1 for red. All right, so I am considering here BGR images, right? What are the primary colors as we were taught at school? In the school, your arts teacher told you what the primary colors are. What? I think red, yellow, and blue, right? These are the primary colors taught by the arts teacher. What's the difference between these 2 color schemes? So this is applicable when you draw something on a white paper, that's called subtractive color space. You're given a white paper. In white means all the colors are present. If you take a red pastel and draw on it, what you are doing is you remove all other colors reflected except red. So that's the subtractive color space. But if you take a computer monitor or something, it is black, and you add by lighting up the blue LED, green LED, and the red LED. So that is the additive color space. That's why that is the reason for the difference between color spaces. So if we access a pixel at locations such as 2, 3, we will get 3 values: the B value, the green value, and the red value. Each value is in 200, 255. That means 2 to the power of 8, 2 to the power of 8 times 2 to the power of 8 different colors are possible with these 8-bit numbers. Altogether 24 bits per pixel. 8 for R, 8 for B, 8 for G, 8 for R. All right. So now what is the difference between the resolution and the DPI? Resolution is a property of the image sensor or the CMOS. So if you take number of pixels in an image, width and height is the resolution of an image. But if you take, for example, 1920 times 1080, actually I should switch these two. 1080 by 1920, full HD, there are about 2 million pixels. Impacts the image detail and sharpness, file size, and the processing time when you increase the resolution. Dots, what is dots per inch? Number of printed dots in 1 inch, that is a physical point intensity. Typical values for a screen, if you want to just see in the screen, 72 dpi is enough. But if you want to print, 300 dpi is required. So let's do a small computation. Let's say that you have a 600 by 900 image. 600 by 900 image. If you print this at 300 dpi, what would be the size? 300 dots per inch. Okay. So in vertical direction, right? In the vertical direction, there are 600 rows. In the horizontal, there are 900 rows. So we need 300 pixels per inch. So that will result in a print of what would be the size? 2 inches high and 3 inches at 300 dpi. So if you don't print at 300 dpi, you will see pixelation. It will look very bad. So when you print, if you want to print, at least 300 dots per inch is required. So to have 300 dots per inch, you need a large sensor size, a high resolution image. That's why when you want to go large prints, for example, wedding pictures and so on, you have to use a camera, a very expensive camera with a large resolution. Yeah. Any questions about this? Okay, so now let's start creating images. So very simple. So you use this package called OpenCV in Python. So first of all, I'm going to show you how to do this thing in Google Colab. And then I will show you how to get your Python system installed in your own machines. So this is the image that we are going to create. We are going to create a black image of 6 pixels tall, 6 rows and 8 columns. And we want to color pixel 2, 3. Yeah. Okay, let's do this now. So to do that, you open your Google and then you can type Colab. Of course, you have to be logged in. Okay, Colab. So you have to be able. You should have a Google Gmail account for this. So you type Colab to say collaboratory, Colab, and search for that Colab to say collaboratory. And welcome to Colab. You click that. Professor Buddhika has told me that you have done these kind of exercises. So you will say new notebook. it will create a notebook for you. Okay, whatever. Then let's do this exercise, and there's a question also. I will answer that question. So now in these are called cells. In these cells, we type code and we click this button to run it. Okay, so import CV2 as CV. This is the first line. Can you get this done in ChatGPT? Yes, for sure. So why are we doing this? Because our learning is much more important than the code. Yeah, okay. Import CV2 as CV. So we will import NumPy also. Import NumPy is a numerical package as NP. These are short names. CV and NP are short names. So I'm going to create an image. Image im equals np.array. np.array. Yeah. The size that I want to give is 6 rows and 8 columns. So I had to give that in as a tuple in parentheses, and I had to give the data type also. D type as numpy np uint 8, not unit, uint. What is the meaning of unit? Uint, unsigned integers of 8 bits. All right. Data type. Why? Because this is how we represent images. So now the image has been created. Now I want to take the pixel 2, 3 and assign a high gray value to that. It's at 200. The maximum number is 255. Now I want to display that image. I will use matplotlib for displaying that image. So import matplotlib.pyplot as plt. Import that, and then I want to display this plt.imshow image, and then I have to give the color map, and because otherwise it will give the show in a different color, and the minimum and the maximum. So cmap gray, I'm displaying cmap equals gray, and then I have to give the minimum and the maximum value. Otherwise it does not know what my minimum and maximum. Vmin is 0, Vmax is 255, and plt.show, that's fine. I want to, yeah, I think that's enough. So let me look at the slide to see whether I have added any other things. Yeah, set tick position. Yeah, that is also important, right? Set tick position. I have to set the tick position at the top. So then we are fine. Yeah. So these are intuitive things. I don't know. Did I properly type that? Let me check again. Oh, x-axis set text. Yeah, this need not get copied, I think. X-axis. Okay, shall I do it exactly as I have done in the slides? I will say fig ax equals plt dot subplots. You figure size also subplot only one figure, and fig size is 6. Let's call it 6 by 8. So we will get a nicer picture. 6 by 8. That's done, and then in this ax, I will show that ax dot x axis at tick position top. This I don't need. All right. So I created an image and I'm displaying that. So let's click this run button. Spelling mistake. 5 dot. Hmm. I don't know what has happened. So let me look at the code that I have in the slide. Oh, I want to say empty zeros, not array. I want to say zero. Zero array. Empty zeros. I'm sorry about that. Okay, now it's okay, right? So you can see at 2, 3, it has put a gray value of about 200. So if I lower that value, maybe I put 100, you see it will become darker. Become darker, right? So 255 is the maximum. It will be the brightest. Okay. So you can see the idea. So you can please do this and manipulate this a little bit. Please take some time to do that. Then I'll answer this question. It's an important question. Is this the reason printers use CMYK color instead of RGB? Yes, exactly. That's the reason. The printing process is in the subtractive color space. What that means is they use white paper, and from white paper they subtract out colors. So CMYK is better for that because the inks are there, so that they can use this, and the combination is also better. But these are for regular offset machines. But if you take expensive offset machines, there are other colors also. They use not only cyan, magenta, yellow, and K means noir, I think, color black. But you have a large number of colors machines. So if you think about offset machines, so you can why is CMYK used in printing? CMYK is standard color model used printing. It stands for cyan, magenta, black. A key, not noir key. Printers layer these 4 ink colors in varying percentages on which white background, absorbing light to produce a full vibrant spectrum of colors. So subtractive color model. So black is also required because just combining this does not produce dark black. So you can read more about these color space and so on. I don't know too much to talk about them. So if you take offset printing machines, you can see some machines have only 4, 1, 2, 3, 4 for the CMYK, but there are, you can see machines that have 1, 2, 3, 4, that like a large number of inks, They print one color at a time, these machines. You can see the paper going through them. The files is looking. I don't know.
මට කිරිතේ එකක් මට උකුතේ එකක්
මට
Okay, so please do the coding. Thank you for that question. Does anyone need more time? Or are we okay? I hope you're okay. Then let's do the color image. So you press code here. So you can go for another cell, right? And you will need exactly the same thing, but I will type it so that you also get used to it. Import CV2 as CV. This is the computer vision package of OpenCV. Import NumPy as NP. So this is the numerical package. Import matplotlib.pyplot as PLT. So now this one is a color image in CV.zeros. So now because it's a color image, you can create 6, 8, 3. What did it do? 6, 8, 3. Now it's a color image. Here you can see that's what I have done. And then to 2, 3, in 2, 3. Now I had to give three numbers to represent R, G, and B. So let me try this. So some red, 200, some blue, 100, some little bit of green, 40 something, BGR. There's a thing about this color that I will talk about later. So this image, because it is done in NumPy, it's RGB. Yeah? BGR is for OpenCV, this is RGB. Then showing that. So for showing code, I will copy. So I will write RGB. Using NumPy. NP.zeros. Okay. Then we can see this color. I think too much green. Oh, I don't want green. I don't want green to be 0, but blue to be under 50 or something. Then you get a pink. Yeah, you get a pink here, 2, 3. So you can see by combining this, you can get different colors. So I'll let you get that coded, please. Please do this. Don't be not coding. Please code. Is everything good, or do you have any questions about this? Okay. So I think now you know how to create a color image also. So if you get the shape of this, I can write im.shape and print it. You will see it's a three-dimensional 683. Can you see that? It's a three-dimensional array. This is a two-dimensional one. This is grayscale one. Color image. So you can put comments also in this. So I can write grayscale image. Here it's a color image, right? I can put text elements. Color image. Grayscale image creation. Okay, now we want to open an existing image from the drive, Google Drive. For that, I have to mount the Google Drive. So if you want good images, I have given you a good set of images in your post. So in this images folder, you can see I have images. So I have linked an image with this folder here because some images I use and maybe also you also own them. So you can see mr.jpg is there. So let's open that image and see. So let's open that image using OpenCV and display it. For that, you need to mount the Google Drive. So that for that I do not know the code. So I will write an AI command for that. Mount my Google Drive and see what it does. So it gave me the code from Google Colab import drive mount. Then I hit run. Then it will ask me say, permission because you are giving this code page access to your Google Drive. So that's why it's asking permission. So you have to click OK, continue this, that, and so on. Now, and then after that, it's mounted. Now it will do this thing. It's mounted. So it's mounted at content drive. So you can see the thing here. So your drive is there, content drive. Under that, my drive is there. Under my drive, I have a folder called images. There, I have these images. This is the images. This is images. So in this images folder, I have all sorts of images, including MR. So this is what I'm going to open now. So I will open using OpenCV code, import CV to as CV, and I will display it using matplotlib, import matplotlib.py.splt. I have say im equals cv.imread, imread, in read, and I had to give the drive location. So we have to carefully give that content drive. Then under the drive, I remember I think we had then drive, my drive. My drive there I had then foldable images. There I had Emma. So okay, it is always good to see whether this image has been opened. So I always assert that. Assert im is not null. Assert that. To see whether this image has been opened. So no problem, image has been opened. Then I can display that. Yeah, so like this, and then show it. It's not grayscale, so I will remove this part. But you will see that image will not be nicely displayed. Access on top, let's find. So, see, colors are horrible, right? Colors are horrible. What's the reason? What the reason is this? Okay, so the reason is this. I'm opening the image using OpenCV, displaying the image using Matplotlib. OpenCV's color space is BGR image. Matplotlib thinks that it is RGB. So we have to do this conversion. So cv.cvt color cv dot color BGR to RGB. This conversion is required. Otherwise, because of this color space problem, you don't get the colors properly displayed. And then I think it will display properly. Yeah. So now you can see it's a 800 by 700 something image. Beautiful image. So I hope it is clear how we mounted the drive and opened an image and displayed. So you can try that on your own. If you have any questions, please don't hesitate to ask. If you cannot get it working, if you share the screen, I'll be able to diagnose and help you. If you want, I can put this code in your chat. So if you make a mistake, you can find that out. I'll put that in the chat. Any questions up to now? Okay, I hope that these things are okay. So what we did is we created the grayscale image, we created color image, and we opened an image also. Image opening also we have done. So we can see the convert color thing has been, I have done that. Why do you need the CV convert color only when displaying using Matplotlib? The reason is the OpenCV color representation is BGR. Matplotlib thinks that it is RGB. That's why the colors get switched. Using OpenCV itself you can display, but using Colab you cannot do that. If you have it installed on your computer, I think you can use, you can use cv.name window and display it in OpenCV also. It has a rudimentary image display. Okay, let's move forward. Any questions? Yeah. Display image properties. So you can display image properties like im shape, im D type, im size, and so on. Let's do that. We have already done one or two things. So display properties. Oh, not text. I want coding window. Code print im dot shape. Right. It will display the shape. Print im dot D type. Data type of that. Size. These are the few properties that we can display. You can see the size is nicely displayed, the U in dates and this one. So find out what this means is I think the total number of pixels. Okay. Now, if you let's say that you want to increase the brightness of the image, so that I will show you how brightness is increased by using the cv.add operation. Okay, so I'm going to open a mask image with grayscale. So here itself you can say that cv.imread grayscale. This is fine. So now what I want to do is increase the brightness of that. Let me call this im1 and then im2 cv.add im1 and 100. Right. And display both these images. So we'll have two columns. And I have to say now axis 1, axis 0. So I will remove the ticks. I'll remove the ticks later. When you display images, it is very important to do this in grayscale. We will give the color map and the vmin and vmax. Okay. So you can see, oh, I took the grayscale impan. I did not display impan, right? Image 1, the brightness, it has been brightened, that's fine. But instead of that, if I do this, im2 equals im1 plus 100, there will be a problem. See, the parts of her face that what has happened here? Can someone answer? Only requirement is to understand that line, two lines. What is wrong here? Please answer this question. I'm sorry. What is wrong here? What do you think is wrong? What do you think? Can someone answer? Try to answer. Okay, I'll give you the answer. When you add 100 here, for bright pixels, let's consider pixel like with the intensity 200. And we add 100 to that. The answer is 300. 300 cannot be represented using an unsigned value. Viewing date. That's the reason. So it overflows. So therefore, we had to use safe operations. Unlike that, this one is correct. CV dot that. Then this problem will not come. I hope it's okay. So please try this also. Put that in the chat. Any questions or comments, please? Okay. So now, one thing is we are going on this programming thing. It is really required for this. Without the programs, you cannot do this. If you do not know Python, I have linked a tutorial in this in your course. Here, Stanford Python NumPy tutorial. So please do this. It will take 1 hour or so for you to complete this, 1 or 2 hours maybe. But you learn a lot. Learn a lot. It's oh, I think wrong one.
So I'm writing an essay on cats. Cats in art history. I'm an art history major, and this final is due.
Hello everyone.
This one is to
In this video, let's look at how to install Python
on your computer. I
The
created
other
that for you. That's sometimes wrong. This is the tutorial that I want you to do. Very easy. I'll edit that in your Moodle because there's a mistake in my thing now. It is correct, right? Maybe I clicked the wrong file. So please do this tutorial. It's very easy. It takes maybe 2 hours for you, and you can all these things like data types and so on of Python and NumPy. It will teach you in very short time. And I have linked a video also here. In this video, I'm showing how to install Python, NumPy, OpenCV, and I think maybe even TensorFlow, PyTorch on your computer itself. This one. So please watch that and get a system installed on your computer. From this point on, I'm not going to use Colab. I'm going to use my own computer and do this thing. Yeah. So that's what I'm going to do. So you can see I have VS Code installed. So I will start a code folder in the folder that I have for this course. Code. Then will open that using VS Code. Okay. So you say file, new, open file, open folder, file, open folder, and navigate to the folder where you want the codes to reside. I want the code to reside here. And open that, there's nothing here. So I can put Control Shift P. So this you can learn on your own how to use Visual Studio Code for this. Create a new Jupyter notebook. And then I can save it. 5218 in class 2026 517 do basics and point operations. Basics and point operations. Okay. So the two codes that I did on Colab, I will copy and see. Creating a grayscale. Exactly the same thing can be done here. So yeah. So all the things I described, I think, are in the video. Yeah. So that exactly the same thing that worked. So we'll copy the other one also, so that I have one file that I can share with you. Right. I will share this file also after the class. I won't have mass only. Getting a color image. All right, that's done. Then opening the Emma Watson image. So now you can see the drive mounting thing is not required. I have to know the location where my images are there. So I have located somewhere. opening an image and displaying. So here I need to know where I am putting this. So this one, I the asset one is very important in this case because sometimes you make a mistake with this path. So I wrote the path properly. So my images are in a folder. I have to go up one, up again, okay, up again to teaching, up again to this one, and there is a folder called pictures, and in that I have a folder called it. This is where I keep all my images. So I don't, because I don't repeat and use the hard disk space. So there you have the image model. You can try with different images, and you can see how this folder thing is managed. Okay. Then we did the addition of colors, increasing the brightness. So here we can see this one. So I'll copy that path down. Increasing the brightness. Okay. So here I will replace this with this line. All right, so yeah, I'll create 3 axes like number of columns 3 and give the original, this version, and image 1, image 2, and let's call this image 3 and display all 3 images. In 3. Okay. So you can see, oh, what has happened here? Oh, I did not open them in color grayscale. Okay, so you can see the difference. Or maybe we can increase this a little bit large with 10 and 30. I think it's too large. Yeah, beautiful, right? Okay, I hope it's okay for you. This file I will share after the class. Okay, so now what we want to do is, I hope you can understand the problem with this one I described. That you can use the for loops to do this. For loops are not recommended in these interpreted languages. So you can see one for loop for the rows, for loop for the columns, and then you can add 100, but don't use it. So I will not code that also. And then obtaining one color plane. So here, if you open an RGB image, you know that blue, green, red are available. So here, what I would do is I will do a trace operation here. What I am doing is, you can see in this indexing of NumPy indexing, we had the image. I create a copy of that image called in blue. Okay. So each of these coordinates can be accessed. If I put a colon, I'm saying all the rows. Okay, that means all the rows. If I put a colon here, I'm saying all the columns, right? So what am I saying here? All the rows. All rows, here all columns. And the last index is the color plane. So here I'm putting the 1. 1. What does that mean? Color plane number 1. Color plane, not 0, but 1. What does 1 stand for? Remember, this image has been opened using OpenCV. So therefore, the color planes are BGR. Blue, green, and red. So if you access the 0th color plane, it will be blue. If you access the color plane number 1, it will be green. This will be 2. Color plane 1, that means blue. I'm sorry, that is green, right? So this is green. This one is green. Which one is this? The second one is red. So I am selecting the green plane and putting 0 there. Red plane and putting 0 there. So that means only the blue will remain. So your image will be seen in blue. Yeah. So this is what we're going to do. We are going to open this image and apply this. Extracting color planes. So let's open, I hope I have that image. So I want to open that as a color image. That means I'll copy code from here. The image I have, I think, is, I have great collection of images, okay? RGBflowers.jpg. RGBflowers.jpg. Let's see if it opens. It opens. So now I'm going to say in blue is a copy. Then 001, I'm going to do that. So yeah, then green, so 0th one, and then red. Then the showing things. Green. Let's display the original one also, right? 4. I'm going to put in red here. Green here. Original image there. Off. This is off. This is off. Show. You can see the corresponding images. You can put titles also. I think we don't know how to do that. I think set you have to use set title command. Set title original, yeah. Channel, head channel. Okay. So you can see that the colors are okay. The color prints have been extracted. Any questions about this code? Okay. We'll briefly look at the cameras and then take another break. So when you have this cameras working, so light is coming in, and then you have inside the camera, these are called DSLR cameras, digital single lens reflex. Now there are mirrorless cameras also. So the important thing to this number 11 is actually the reflex and relay mirror. So usually the light is going to the eye through this path, but when we do the click, the mirror will open and it will strike the through 7. Yeah, 7 is the shutter, and 5 is the color and infrared filter, and then 6 is the digital sensor. That's the CMOS sensor. That's the important one, and so on. So you can see you have the shutter, the color filter, and the sensor. So that color filter is like this. So it will have what that means is like if you take the red filter, red colors will transmit only for this location, this location, this location, and so on. Green light will transfer through this location, this location, this location. Blue with this, and so on. So you can see this color filters out colors, and different pixels in the sensor array get different sensations for different colors. Different colors. So therefore, if you take some pixels, they don't have the blue. Some pixels don't have the green. Some pixels don't have red. So therefore, you have to interpolate like so. This is called demosaicing. It happens inside the camera. Estimating the missing component from neighborhood values. So yeah, that's the important point that I want to bring here. So when you think about the color, the visible spectrum of light is from 400 nanometers to about 700 nanometers. And you can resolve that using a prism. So additive mixing is this. subtractive mixing is this. We looked at that, BGR versus CMYK. And the color model, color space, or color system facilitates the specification of color. That is the coordinate system and a subspace within that system, such that each color in the model is represented by a single point containing that subspace. RGB, image capturing in cameras, wavelength bit. CMYK, cyan, magenta, yellow, black for printing. HSV, hue saturation valuing, how humans describe color. Decouples the color and the grayscale information. So I will describe only one of them. So this one, HSV. So here you can see the hue. Hue means a color like green, red, pink, magenta, cyan. You describe the color by name. And here the greenness of green. So if you move in this direction, the blueness of blue will increase. But it is a brightness. So if you go down, this axis, the brightness will decrease. Although it's some blue, the brightness will decrease. So that's why each of these color spaces are different. So if you're interested, you have to study about them. My knowledge about these color spaces is not too high. So in summary, what we discussed up to now is grayscale digital image is an array of 8-bit unsigned integers in 0 to 155. We call each integer pixel. Color images have 3 such arrays, one for red, one for green, and one for blue. We can manipulate images in an OpenCV function or a pair of for loops. That's what we sort of studied. Then we will look at sampling and reconstruction after a break. So we will take a break and we will meet at about now it's 11:37, 11:57 or something. We can meet. So I'll post the recording. Under sampling and reconstruction, what we want to do is understand the concepts of the frequency that come in when you think about the amount of information that can be represented using a image of some resolution. So you can see when the resolution goes down, the frequency content that it can represent reduces, right? That's what we are looking at. So an example, if you consider a sine wave, what if we miss the things between the samples? Unsurprising result is information is lost. Surprising result, indistinguishable from the lower frequencies. So what this means is now you can see this black sine wave is of a high frequency, right? This black sine wave, high frequency signal. You can see it oscillates faster, right? And now what has happened here is sampling has happened here, here, and so on. So with these samples, to represent those samples, you don't have to draw a sine wave of that high frequency. You can draw this gray sine wave, which is of a low frequency. Exactly goes to those samples. So we can see these samples, because we have undersampled, represents a lower frequency signal. And you see that. So yeah. Or even high frequencies we can draw. So therefore, sampling properly is very important. Aliasing means signal traveling in disguise as other frequencies. Yeah. So these kind of things we have seen. If you look at movies and so on, sometimes you see the wheels rotating in the opposite direction and so on. So you briefly look at that. Because the camera frame rate is 30 frames a second, so sometimes wheels can get frozen. If it's not a stationary, can you see? Did you see that? So, so when the picture is taken, the next rung of the wheel is there. So, next spoke of the wheel. Yeah. The spinning wheel is stationary, so this kind of thing can happen, right? So you can study those things later. You can watch these videos and interesting things. So that can happen in images also. So you can see here, and an image represented at 256 by 256, you can see the black and white pattern. 128 128 sort of okay. 64 by 64 sort of okay. 32 by 32, now you can see things start, crazy things start happening here. So 16 by 16, we don't know, it doesn't even represent this one, right? So therefore, aliasing is a serious problem in images. So you can see disintegrated texture can happen because of that. So that's why you are not asked, you are asked not to wear striped shirts when you go to the TV station, yeah, and so on. So when you take a picture of the screen, these kind of things happen. Aliasing in neural networks is also there. So, but I will not talk about that. So now in this thing, you can see because of aliasing, entire unimaginable things happen. You can see what's happening here, right? So see, yeah. So see, okay. So you can study and watch them later on your own. So we know the Nyquist-Shannon sampling theorem is there. When we sampling a signal at discrete time intervals, the sampling frequency must be at least twice as the maximum frequency of the signal. I think this is a basic thing that we learn, right? Input signal to allow us to reconstruct the original signal perfectly from the samples. So if you take now this gray signal, sampling has happened here, here, and so on. This is not that twice the frequency of the gray signal. So therefore, when you reconstruct, you can draw this black signal there, which is entirely incorrect. So this is good sampling. So there, for this one, only signal that you can draw is this. So this is okay. This is okay, right? So can you see that? How do we get rid of sampling? Aliasing. So sample often, you more often, that means do high frequency sampling. Or get rid of all frequencies that are greater than the half the new sampling frequency. We lose information, but that's better than aliasing. How to get rid of high frequencies? You can use a filter. So in audio also you use filters. I think if you have a microphone here, we do a low pass filter, then only we do the A to D conversion when you write it into a CD. So this is important when you have phones also. In phones also, the sampling rate is 8 kilohertz. So therefore, you cut off the frequencies beyond 3.4 kilohertz using a filter. And then in regular land phones. So yeah, this is the thing. So here also, yeah, you can see the sampling. So for images also, this resampling and interpolation, this is important. Now think about this. Now sampling and subsampling an image. How do we reduce the size of an image by a factor of 2? How do you reduce? And now assume that these are the pixel centers. These are the some colors are there at those pixel centers. Right, values are there. Image values are there here, here, and so on. Right. What we want to do is we want to get rid of some of those pixels. That means about throwing away every other row and column to create a half-size image, like so. Is it correct? It is not correct. Why is it not correct? If you do that, there may have been high-frequency signals in that original image that cannot be represented with this kind of a low sampling rate. So therefore, you have to first of all filter, get to the high frequencies, then only subsample. So subsample without pre-filtering. So if you don't pre-filter, so if you take half, 1/4, and 1/8. So if you keep says, you get crazy patterns start appearing that were not there in the original image, right? So, but if you subsample using a Gaussian filter, at least the crazy patterns, of course, we lose information, but at least the crazy patterns do not start appearing. So here you can see the giraffe image. So this is the original image. But if you downsample by 4, you can see because of this pattern of the fence, you can see crazy things appearing here. But if you downsample smooth first and then downsample by 4, it is better. So filter or using a smoothing filter, then do the subsampling. Yeah. So how do you do the upsampling now? Okay, we discussed about downsampling. You have to smoothen out. Then how do you do upsampling? So let's increase the resolution of the sampling rate. So like so, but then Now for these places, we have to compute the value that should come at these places, right? Compute the value. But if you want increase the size by factor of 2, it's easy. You can add this and this, sum them, and you can just divide by 2, right? To get the value here. You can use these two to add and divide by 2, add and divide by 2, add and divide by 2, and using these two, maybe you can add and divide by 2 to get this one. So this is called interpolation. So what should the value here be? So we need to interpolate. So there what we do is f.5.5. So if you put ABCD numbers there, so half A plus B, right? I think you understand that. This is half A plus C. This for this one, you can add all the numbers and divide by 4. This is very easy if you want to upsample by a factor of 2. But if you now in demo seeking also this is required, right? I showed you at the very beginning today. But if you're upsampling by 3 times, not 2, then you have to slightly think about it and use so-called bilinear interpolation, which is a more general case. So I have given you the formulas, but it is very easy to do this. If you know the ABCD numbers and the ratios, it is easy to do. And then there's a more advanced one called bicubic. Let's see the effect of that briefly using a GIMP. So Photoshop, if you have Photoshop, it's expensive. You can do something with that also. But let's do that with GIMP. I will open a very small image. It's too large. Okay, I think I'll be able to show the effect with this image. I'm going to open that using GIMP and apply that. This is my GIMP. If I open, go to that folder. Yeah, so you have to this is the thing about this kind of software, you have to navigate to those folders. It's not like not as easy as using Photoshop. Yeah, sorry that you have to watch me navigating to the folder. Open too small. Open this image. So we can see to upsample, we can say image, and we can scale image. So when you want to scale the image, so I can scale by a percentage. So let's say I want to scale it by 500%, something 5 times percentage, and then you can choose this, right? Non-linear, cubic, and so on. So I think none will give you nearest neighbor. I think I don't know. So you can see the pixelation effects and so on there. If I upsample scale the image using 500 times, using bicubic, cubic, okay, cubic is better. So you can see that lines have nicely come, right? Okay, so I think you understand the effect. So you understand, so you can manually implement these equations also, but I will not talk about it now. Now let's look at the intensity transformations, a very important topic. Now let's take the very first intensity transformation and I will explain you what this means, what this graph means, and then we will be able to code that. So what this graph means is this. Now here is an input image fx. So I just have x to represent the coordinate, right? Where it is like 2, 3, pixel 2, 3, and so on. So this is gx is the output at the same coordinate. So we have a transformation. That transformation is signified by the values. The transformation happens to the value of the pixel, yeah, not the location. So this is called the identity transformation. So that means if you have, very easy, okay, if you have a pixel of value 150, we go there and we check what is the output pixel value. Output pixel value is of 150. That's why we call it identity transformation. So let's code this. So here is the code. It's very easy. So I will code this and explain you what that identity transformation means. Okay. So what we want to, I want to give you the technique of doing this. Identity transformation. Okay. First of all, we can open Emma Watson's image. The grayscale is fine. And original version and the transform version, that's what we want. So I will copy this whole thing. Now I don't think you need this anymore. So I need only 2 pixels, two. Yeah, that's fine. Okay. All right, now I have the image, so I'll call it F so that you can relate it to the slides. Okay, F is the original image and G is the transformed image. Okay, so this transformation is a line, right? So that line I'm going to define like this. So NP arrange 256. I will show you a graph of that also. Oh, I like to have 3 of them. 3 of them to plot the graph here. Okay, the transformation T is equal to NP dot arrange 256. But I want a data type as you int 8. So you int 8, that's all. So this T is a line. So I will plot that T and show you. Maybe I'll comment them out first. Plot T TLT this is okay. So you can see this is the transformation. If it is 150, I get 150. That's all I want to show you. So that is T. Your construction of T is okay. So if you just print T and see, let me print it and show you. So T, I'm printing that. So numbers like at location 0, it has 0. At location 255, it has 255. If I access that by the location, it gives me spits out the same number. That's why it's called identity transformation. So now the most important thing is this. The way to apply that is I get G by indexing T with the input image. Yeah, that's what I'm doing. So nothing will happen. All right, so yes. what happened here. So 750. Scale it up so much. I don't know. So this is okay. I think nothing happened. So this transformation also I showed. I don't know how to get that displayed. That's all I think. Oh, now it's okay, right? Yeah. Okay, now I know how to do that. Okay. Okay. Yeah, so you can see because of this identity transformation, nothing happens at 150, you get 150. So now you can see if you change this transformation T, you can do wonders. This is what we are going to study. Next we are going to do the next we are going to do the inverse of that. That is called the reverse of that. So I will show that now. So the same thing, only the transformation has to change, but I will display using OpenCV now. This is the negative transformation. Negative transformation. I agree. Bring the code here. Now NP arrange 256 will give you the positive transformation. So NP arrange, so we have to, for the negative one, the coding is slightly different. 255 going up to 0, you have to put -0 and in steps of -1. That's what you want there. Starting from 255. So if you do not know these things, please refer to the tutorial that I have given. It's very easy. In 2 hours time, you will learn all these things, these syntax. Okay. So now let's do this, and I will show you what T is, right? Yeah, I can plot T and show you. Plot T. So you can see the negative transformation, right? So we apply this. So I will display that using OpenCV. cv.named name window. Let me say image or something. The normal. Okay, that's okay. Here I'm going to use different image. I'm going to use the image of Katrina. Katrina. Oh, all right. So let's see. This one here. Okay. And then as a first image, I'm going to show dot Kim show. And I have to give the window name image. I'm going to first of all show F, the original image, and then I'm going to do CV wait key. prompting me too far, too much, I think. Wait key 0, so I'm going to wait for a keyboard input. Then I'm going to cv.destroy all windows. Okay, so show the first image, show the second image, and done. Okay, this is the transformation. Oh, transformation, top step. Okay, yeah. So I hope you are ready to visualize this. Okay, this is the first image. I hope you are ready, everyone. Please watch. So when you have do the transformation, and did you see it? I hope you saw it. So I'll do that again. I know that you want to see it again. 1, 2, 3. See? Oh my goodness. It's scary, right? Yeah, okay. If you're not happy about this, I can do that for another image. Also, I have another image, a very famous person. Okay. This one. Do you want to see it? Can you see that? Oh my goodness. So you can see that using the intensity transfer, we affect the individual pixel values. And that's what we want to do. So the way to do that is this: use this transformation as a lookup table. So if I explain that further, what happened here is this. Now, when we have the transformation here, my T, all right, will look like this. It started from 255 at location number 0. Yeah, its value is 255. At location number 1, what is its value? 254. At location number 2, what's the value? 253. At location number 3, 252. Okay. At location number 255, last one, its value is 0. So in this operation, where I write T index by G, right? T index by F to get my G. What I'm doing is I'm getting the individual pixel values of F. If the individual pixel value of an F, okay, is let's say pixel value is of the one is, let's say 2, right? What does the computer do? Computer will look at the location number 2 of this. Location number 2 of this array is this one. This is location number 2, right? So it will spit out 253. So the value of G at the corresponding location will be 253. You can see I'm using that T as a lookup table, and I'm indexing that using the input image F. Input image F. I'm using T as a lookup table. So because of that, I can use CVLUT for this and do that. So this is the idea. If you have a question about that, you can always ask me how it's done and what is the meaning of that. Okay. Then next we can do a lot of things. So now you can see that you can create so many crazy transformations like that. So this one I created this transformation. So I have it's a piecewise continuous transformation, 3 lines. So individual lines I coded as T1, T2, and T3. Okay. T1 is from 0 to 100. So these breaking locations I coded them 150. This coordinate is 150, 150. And this location is 150 to 100, 150 and 200. So now because I want to convert them into an array, I have to get the equations of those lines. The first line's equation, I somehow got it, okay? Got it and I wrote T. Second line's equation, I got it and wrote, and I combined them, T1 and T2 combined, and combined T3. So now finally I have the transformation. That using that I here use CVLUT, otherwise you can just use transform and into that input effects. So the same thing. So these are easy things, and then there is a thing called gamma correction. So from this gamma correction, what you can do is these are transformations defined by the image raised to the power of gamma. But of course, here we have to normalize the image to 0 and 1 first of all. So, for example, if you take gamma like 5, you can see a large, now these intensities are dark intensities because 0 to 0.6, right? These are the dark ones, these are the bright ones, right? A large range of dark pixels is compressed to a smaller range of dark pixels. Then if you take bright pixels, a small range of bright pixels is expanded to a larger range of bright pixels. So this enhances the brighter areas of the image. If you take gamma equals 5. Opposite, if you take gamma equals 0.5 or something. So here are images. So I have the original image here and the gamma corrected version here. So the different values, the gamma equals 0.1, and you can see totally becomes you cannot see any. Gamma equals 0.5. If you see, you can see the darker areas in the image are enhanced. You can see them properly. So gamma equals 0.5. 5, we saw that the bright areas are enhanced, right? In this image, the bright areas like this, you can see that they have been enhanced. So this is the effect of gamma correction. So I have given you the code here. The code means how to construct T. So I have constructed T using a comprehension. So since this Python thing you are not very familiar, so I want to stop here and I want to allow you to briefly learn Python by going through the tutorial. Please do that. And next time also I will revisit and show what these corrections are. Then they have few more things to learn about intensity transformations and we'll be done. To answer the quiz, you lack a little bit of knowledge, but I extended. So please go through the slides and try to answer. These quizzes do not carry that many marks. This is just for you to practice them. Yes, I will stop the recording now and I can answer any question.